Okay. Hello, my name is August Welch. I'm a geologist with CBM Smith. I am here today. The person that was originally supposed to give this talk Zoom called me 2 days ago and said he was having a family emergency and he needed to go down to California. Good news is everything's okay. He just needs to go down and help his grandmother. So he called me and he said, August, you spent a lot of time at Well 12A. You know the site like the back of your hand. You spent thousands of hours in the field there. Can you go give this talk for me? I said, of course. Being a geologist, I like to say often that I'm sort of a jack of all trades and a master of none. So I'll go with this talk, and forgive me if it's a little bit rough around the edges. I've only had a few days to look at it, but we'll do the best we can, and hopefully be able to bring you some experience. One of the things that I can bring to this talk is that because I've spent thousands of hours in the field over the last 7 years on this site, I can share with you some of the real world experiences and lessons that we learned in the field, and kind of talk about how these projects sort of get implemented from the planning phase on paper and then actually taken out and scaled up and implemented in the field. Just a quick presentation outline. I'm going to talk a little bit about the site background, and then the design and installation of our thermally enhanced bioremediation system, that system operations and monitoring, and then we'll talk about the results. So the Well 12A Superfund site is right up the road here on South Tacoma Way. This was a former time oil recycling facility that operated in the 50s, 60s, and 70s, and let's just say that they might not have had the most responsible environmental practices. One of the things that they did in the oil recycling was they generated a filter cake material that they essentially would use solvents to squeeze out this filter cake, and that was part of the oil recycling process. So they, like anybody would do in the 1950s, you take your waste filter cake product and use it as fill on your site. So they kind of spread it out around the site, and that's kind of the little blue area up there. That was kind of our primary source area. In 2010, we went out and started the preliminary design investigation. We did that work as part of the EPA Superfund site and on behalf of the United States Army Corps of Engineers. We went out and started to drill some holes and kind of really get a handle on where we were going to design this thermal treatment system. We had a goal of essentially defining the thermal treatment system as the area of 10 ppm of our focus COCs. So those focus COCs are PCE, TCE, cis and trans 1,2-DCE, vinyl chloride, and 1,1,2,2 tetrachloroethane, or PCA. We decided to go out to this site with sonic drill, which was a really great choice, I think. Past work that had been done on this site had varying success with a hollow stem auger, and one of the things that we noticed immediately when we started to look at the data was that a lot of the hollow stem auger data, you end up with a kind of a cross section that says 110 feet of sand, silt, and gravel. It's like, okay. So one of the things that we really like about using sonic drilling for this type of application is you get a continuous core. And as a geologist, you love a continuous core, especially when you get it from multiple boreholes, because you can lay it out and you can look at it and you can start to become friends with the stratigraphy, and you can start to define the units. I showed up at this site as a young geologist in 2010, and just basically got a call. Hey, August, can you come to this site and drill a hole? Sure. Very first hole we put in, we got down to 30 feet, and we came up with a clean brown sand with some pebbles, and I just took one look at it and said, this looks like QVA to me. And the guy I was working with looked at me sideways. QVA? I said, yeah, it looks like QVA. So I've never heard that here. So sure enough, I went home that night and I pulled out the South Tacoma 7.5 minute quadrangle and started to look at the geologic map, and you've got Stilcombe, gravel, QVA, and pre-Fraser deposits. And we started to immediately define the stratigraphy, which we carried that stratigraphic definition all the way throughout the remediation, and it became very useful in how we started to talk about what our target zones for treatment were. Disadvantage of sonic drilling is that it generates some heat. because the purpose of our design investigation is to define an area of 10 ppm, we're not really worried about compliance here. What we're trying to do is kind of get a gross picture of where's our source area and where do we need to define the treatment system. So we don't think that heat that's generated from sonic drilling is really a significant problem in how we ultimately design our thermal system. So I just put a plug in there for anybody that's interested. Going forward on these types of sites, using sonic drilling can be very valuable. It's especially valuable when it comes time to start defining what your site stratigraphy looks like. We'll talk about it in a minute. There's a silt layer at this site, which was a key player, and in some places it's only a few feet wide. You can imagine if you're drilling a 110-foot hole and you're doing split spoon samples every 5 feet, you can very easily miss that silt layer. And it turns out that was one of our primary target treatment zones. So very important to be able to see the entire section of lithology. At this site, we used, essentially our remediation goal was a 90% reduction in contaminant mass discharge from the source areas. The way that we measured that at this site was we already had a groundwater extraction and treatment system. And we were able to demonstrate that treatment system gave us complete plume capture. So we were able to use that existing treatment system to demonstrate what our baseline mass discharge was, and then at the end, get our post-treatment mass discharge and compare that metric. And just a spoiler alert, we were essentially successful in meeting the 90% mass discharge criteria. This is a sort of a cross-sectional site that was developed in MVS that kind of shows our thermal treatment zone up on the upper right-hand corner and the former time oil building. You can see there the distribution of the contaminant at the surface that was a result of that filter cake that was used as backfill. And then below that time oil building, you can see the zone where the heavy phase of the contaminant went down. At this site, it was kind of interesting. What we had was not in the source area, our primary source area, we had not a DNAPL or an LNAPL. It was essentially, it was a neutrally buoyant NAPL. It was a mixture of waste oil and petroleum products and chlorinated solvents. So what we found was that it wasn't necessarily floating. It was kind of bound up a little bit below the top of the water table, and it was a little bit hard to define in some places because it just sort of had this neutrally buoyant characteristic. It didn't want to float. It didn't want to sink. It was just nasty. And then you can see the groundwater plume as it heads down gradient. At this site, there's a very strong vertical groundwater gradient. It's on the order of like a tenth of a foot per foot vertical. So the horizontal gradient at this site is essentially flat, and so most of the flow path at this site is actually downward. There's an aquitard, kind of a regionally extensive aquitard at about 110 feet, and we found that some of the flow was sort of stratigraphically controlled as well. But the well 12A is a city of Tacoma municipal well that's located about a half a mile away. And this plume from the site impacted the municipal well. It was discovered during sampling. They put an air stripper on the municipal well. And then, years later, we got the funding to come in and start the remediation. What we found when we were implementing so the original plan was to dig out the surface soil at the top, do a thermal treatment, like a full-blown thermal treatment in the source area beneath the time oil building, and then do an enhanced anaerobic bioremediation of the down gradient plume. So while we were putting in injection wells and pilot test wells for the EAB portion of the remedy, the very first well that we put in, EAB1, I got down to 50 feet to target this silt interval. Well, we didn't know that the silt was there. We got down and we saw the silt. We saw DNAPL on our very first well. 250 feet from the source area, we hit DNAPL. And if you've ever drilled in the field, if you see DNAPL in your boring, it's like seeing Bigfoot. It just doesn't happen. You have to get extraordinarily lucky. But sure enough, we hit that. But we continued to install our injection well network, and during another one of the injection wells, we hit another pocket of DNAPL. And that one was interesting. You kind of had two pieces of silt that were shaped in a V, and you had about 5 feet of sand in between. We called that the sand sandwich. And there was an extraordinary amount of DNAPL mass that was sort of bound up in that sand sandwich. Essentially, we had identified another source that, later on as the project progressed, we realized we were going to need to do something else. The thermal treatment was going to work, the EAB down gradient was going to work, but it might not work for these sort of localized secondary sources of DNAPL that we had. So that's where the thermally enhanced bioremediation comes in. So why do we use thermally enhanced bioremediation? Well, first of all, because there's increased biodegradation kinetics at temperatures between 35 and 45 degrees C. You add a little bit of heat to the system, you stimulate your microbe population, you increase your biodegradation kinetics. Now, secondly, at this secondary source, it had a signature, and we actually believe it was a different release that was potentially not related to time oil, might have been related to previous site activities, but there was a very strong 1122 PCA signature. It was sort of a dead ringer. Now with 1122 PCA, it's pretty, in its raw form, it's pretty resistant to that hydrolysis reaction to take it to TCE, so you can start reductive dechlorination. But we know that if you add a little heat to the system, it helps enhance that rate of the hydrolysis reaction. So using that technology in this scenario was a really good choice. And then, of course, elevated temperatures will lead to the enhanced dissolution of the DNAPL, which is what we're after. We want to have dissolution of that DNAPL and send the mass flux downstream so that the rest of the EAB treatment can take effect on the dissolved phase. The two areas where we had DNAPL are shown, INJ30 and EAB1. We installed several electrical resistance heating electrodes, and we elected to use ERH there because a localized hotspot is, for this type of application, it's hard to control the temperature. If you use ERH, where you have two separate electrodes and you're pushing a current through the formation, it's much easier to control your temperature. And that's important for this application because if you start to get above 50 degrees C, then you can your micropopulation can start to go the other direction, and we don't want that. So this use of ERH allows us to target specific temperature ranges. We installed an array of 3 electrodes around each DNAPL hotspot, and we had some specific depth intervals which target that silt layer that I talked about earlier. This boring log that's shown here is the sand sandwich that I was talking about earlier at INJ30. You got the upper QPF silt and the lower QPF silt. So in the formation, this sits below the Vashon Advanced Outwash, and then below that is pre-Fraser undifferentiated deposits, essentially. This silt layer, we grouped it with pre-Fraser. We called it QPF. We typically just called it the QPF silt layer. Regrettably, there were several borings that we had where I had wood fragments from this silt layer that I wanted to do carbon dating on, but I just never really got my act together. And if I had it to do over again, I would have found a grad student at the UW, and I would have made sure it got done. Would have paid for it out of my pocket, because it would have been nice to know really where this silt layer fits in the stratigraphy. Does it affect the remedy? No, but we're scientists and we like to know these types of things. So one of the bonuses that since we had already done a full-scale thermal treatment at the site, we already had 480 volt 3-phase 480 power at the site. So we were able to hook right up to that and start up this low temperature system. We also installed DNAPL pumps at INJ30 and EAB1. That brings up something that I wanted to share with you briefly. One of the things we learned real quick on this site when we found DNAPL is, normally when we install a monitoring well, we don't really think about putting a sump at the bottom of it. But in this case, when we're drilling at DNAPL sites, we want to have our screened interval, and then below that we want to have like a 1-foot PVC sump. What we did in the field when we realized that was we just talked to the drillers and we had them get a solid piece of PVC and we affixed it to the bottom of the screen with stainless steel screws. In the future, if I'm going to drill another DNAPL site like this, I'm going to talk to the driller ahead of time and make sure that we get, some threaded casing that we can put on there. And I mean, it's kind of a no-brainer. But had we not done that, we wouldn't have been able to recover any DNAPL. But as it was, we were able to put the passive skimming DNAPL pumps in and recover an appreciable amount of product. I don't remember the volumes, but I mean, on the order of tens of gallons of DNAPL that were recovered from these wells. So it was useful. We started up the temperature, and then just kind of, we monitored the temperature of the treatment zone. As you can see, we're targeting that 30 to 50 degree C range. Over there on the right-hand side of the graph where it says operation at the gets, that's when we turned the groundwater treatment system back on to start our mass discharge, our post-treatment mass discharge measurements. EAB1 we ran from August 2015 to October 2016, and INJ30 we shut down in February of 2017. So let's talk about the results. This is just a map showing those two areas and all of the Swiss cheese that we made out of this site over the years. It was pretty fantastic. So on the left-hand side, the EAB1, the VOC molar concentrations, you can see that big spike at April 1st, right before we turned on the system. What we think that was after heating, essentially a lot of the CVOCs get bound up in the oil that we had injected for the EAB treatment. When you heat it, some of those CVOCs get released from the oil. So you see that spike, and then immediately after that, you see the rapid fall off. Treatment was very effective at EAB1. At INJ30, the treatment was a little less convincing, but I mean, really, it kind of just comes down to it's a function of there's a lot more mass at INJ30. That's the sand sandwich. Concentrations are continuing to decrease there, and we feel that we've adequately kickstarted the EAB process there, and that it will continue to decline. COPC molar concentrations at nearby wells. These are groundwater samples collected from down gradient wells. What you see is that after treatment, you see this really rapid increase in VOC flux and in chloride flux, chloride's a great proxy for your total VOCs. And that's great news, because that means that we're having dissolution of the DNAPL at the source area, and that's what we want. We want to dissolve the DNAPL at the source area and send it downstream into the treatment area. Same thing at INJ30. The down gradient wells, after this low temperature enhanced EAB, we see these tremendous increases of mass flux at the down gradient wells, and it's a really great indicator that what we were doing there was working. So just some quick slides about kind of the success story really. 1122 PCA. You can see on the left-hand side that's pre-treatment. On the right-hand side is post-treatment. We have a drastic reduction in the area of 1122 PCA. TCE, just remarkable. Essentially what looks to be about a 90% reduction in total mass of TCE. Cis12 DCE, we also saw some reductions there, kind of less in the source area, but that's really to be expected. Over time, the reductive dechlorination process has started. Sometimes we even see the 1,2 DCE starting to go up, that's because we're removing the TCE and the 112 PCA and converting it to 12 DCE. And there you go. Eventually, same thing with vinyl chloride, trans 1,2 DCE and vinyl chloride. We actually see a small increase in the source area, which is really it's a great sign. That's what we want to see. That means that reductive dechlorination is working. Eventually that vinyl chloride makes its way to ethene and methane. So a summary of the results, we did a thermally enhanced bioremediation. We operated that for approximately 18 months. The total energy of 150,000 kilowatt hours. I'll just throw in a little aside here. One of the things that's been on my mind is, sustainability practices. How do we take, how can we take some of this heat that we put into the ground and pull it back out and reuse it as a kind of a low-tech, geothermal application? I don't know exactly what we use it for. If everybody has any great ideas, ask me at the end. But we controlled the temperatures really well within a 5-degree specified range at our depth intervals. The degradation rates we accelerated both within the DNAPL hotspots and in the surrounding monitoring wells. And the EAB1 DNAPL source was exhausted after 12 months, and the INJ30 DNAPL dissolution was enhanced and declining to a concentration trend by the end of operation. I wanted to add something to this. So we didn't have a slide in this presentation because it didn't specifically apply to this, but one of the key components of the injection that we did here with our EAB amendment was we did this as a shear thinning fluid injection. So we used xanthan gum with lactoil to create a non-Newtonian fluid that thins under shear. The reason that we did that is because at well 12A with sand, silt, and gravel, we have a very heterogeneous formation, and we're specifically targeting this silt interval. The chlorinated solvents back diffuse out of groundwater into the fine grain portion of the silt interval and sort of acts as a sink or an ongoing source for contaminants to groundwater. So we need to target that. Now, if you just take water and lactoil and you squirt it into a well, across a 10-foot section of screen where you've got sand, silt, and gravel and a 2-foot silt layer, where's all your amendment going to go? It's going to go into the sand, silt, and gravel. It's going to follow the preferential pathways. When we use a xanthan gum and we create this shear thinning fluid that thins under shear, you can essentially, the high shear portion, which is the fine grain portion of the formation, becomes the thin portion of the amendment, and you're pushing it into the silt. So you're able to target the fine grain portion of the formation, and we think that that's very important for being able to get contact. So the way we did that was we took a xanthan gum powder, and we took this is a proprietary method, by the way. So, at first we tried a Silverson mixer, we tried all this crazy stuff, and then sort of by accident we discovered, so with xanthan gum, it's very difficult to work with. When you're putting it in water, if you just put xanthan gum into water, what you get is gumballs. It's horrible. It's very difficult to deal with. But what we did was we took the lactoil, we put it in a tote, took the powdered xanthan gum, we added that to the lactoil. There's no water in there. And essentially the lactoil coats every one of the little xanthan gum powder, and we mix that with the paddle. So then you have a powder suspended in oil. And then when you add that to your big, we had a big 20,000 gallon mixing tank. We had 2 of them with big paddles at the bottom. And when you add that to the water, you get your emulsification. No gumballs, just perfect emulsification. And it worked beautifully. We did one of the largest self-performed shear thinning fluid injections ever attempted at the time. We injected close to 1 million gallons over 4.5 months, and we self-performed that. And it was a real success story, and I really feel like we sort of helped to kind of pioneer that method of the mixing is the key. How do you get the xanthan gum into your emulsification? That's how you do it. So I'd also like to thank some of the other people that helped to work on this: CDM Julie Trump, Mark DeSian, Mary Lou. At the beginning, so Tamsin Macbeth, she's kind of the brains behind this remedy. She's with us. She's out of Pocatello, Idaho. She's doing a lot of really amazing work with CDM and Zoom, who unfortunately couldn't be here today. I'm glad I was able to fill in for him. But Zoom is an incredibly hard worker. I mean, I come into the office sometimes at odd hours on the weekends, and it seems like he's usually there, thinking away on one of his projects. United States Army Corps of Engineers, TRS, EPA, so many just wonderful players on this project, and a tremendous success story. So just, I'll leave it with questions. Just a couple of pictures. On the left there, that's EAB1, and you can see our silt layer at the right-hand side of the photo with our DNAPL perched on right at the top of that silt layer. And then on the right was one of the recent compliance wells we drilled, which I just captioned that a well driller's dream. Thank you.